Okay, I'm looking today at the expectation variance of a sample mean. You may recall there's slight issues when you try to find the population mean. Population mean is, of course, what the actual mean is for all the things you're trying to measure. So if I'm looking at, I don't know, fish in the sea, I'm looking at cod, I'm looking at the average mass of every cod in the sea. My chance of catching every cod in the sea to be able to measure its mass and then chuck it back in is rather limited. It's impossible to catch every fish in the sea. So straight away, the chance of me actually catching every fish in the sea means that the population mean is impossible to find. So in reality, I end up finding a sample mean. And the sample mean may be a good and accurate description of it. It may be rubbish, I don't know. But you essentially notice the difference in the notation. So the population mean is mu, whereas the sample mean, we always write x bar. And we are looking at this sample mean today and looking at the expectation and the variance of the sample mean. So whenever we have a sample of results, I've written here, it is natural to believe that the average of this sample will become less spread out than the original result. So let me just see if that seems fair. So I want you to imagine a scenario, and my scenario is I'm going to roll a die 6 times. And obviously when I roll the dice it's binomial. I'm doing it 6 times, and the probability of it occurring, let's say I've done this already, you'll have to take my word for it. I was looking at the number of number of times that 2 came up on the dice, number of 2s on the die that I got when rolling this. And when I rolled it 6 times, I actually did this then a number of times, and I'll show you that in a bit. But let's see what I'd expect to get. You may recall that the expectation for a binomial distribution is NP. So E equals NP, so 6 times a 6th is obviously 1. So I'd expect to get, every time I rolled it, 1, 2. And with the variance, you may recall, is usually written NP, either Q or 1 minus P is the more usual notation. So that's 6 times a 6th. Probability of not getting it is 5/6, which is 5/6 if you do it. So 5/6. That's the variance. Now those 2 answers then are what I would expect to happen. Now I actually did this. I did it into actual fact 4 times. And you're going to have to take my word for it. I actually recorded the results. I've got a dice out a game I had here. I rolled it, well, 6 times, but then I repeated that 4 times in total. And these were my results. The ticks are meant to represent every time I got a 2. So you can see first time when I did it, I actually got 2 2s. But then in the next go I only got 1 2. And then the next go I got 1 2. And in my final go I also got 1 2. And those were my actual results. And so you can see my results were 2 1 1 1. And it's these that I want to find now. I want to find x bar, the mean of these numbers. And if you do that, you obviously add up to 5. I've got 4 numbers. 5 over 4 is 1.25. On average, I was getting 1.25, which is it's a bit bigger than that. And the standard deviation, or the mean, I want to find as well. Now the easiest one is just chucking it into your calculator, and that's what I did. I chucked in my calculator, and according to my calculator it came up on the screen as 0.1875. You may recall how to do it. So I just chucked these numbers 2 1 1 1 into my calculator, and the sigma x squared, it told me the variance is 0.1875. Whether that's a good one to use, there's actually a couple of different versions of the variance, but that's one I used anyway. And the one thing I noticed here was actually, I know this is 0.83, and it was completely, well, definitely much bigger than this one was. And again, I could have made these numbers up, but I actually didn't. This is much lower than the 5/6. So it begs the question, what's going on? And in actual fact then, we can be shown that E of x bar is very similar to, we'd expect it to be equal to E of x. Whereas the variance of x bar is not equal to. In fact, it's equal to the variance of x divided by n. Now let's just go back a step. I got 5/6, which is 0.83-ish. And if I divide it by 4, because I did it 4 times, that's approximately equal to 0.2-ish. So you can see, of course, these are only estimates of what you'd expect to get. But I got 0.1875 with my real data, and you can think, well, actually, it seems to have worked. And I suppose then, it begs the question, does this always hold? In actual fact, it holds for normal distributions as well. I did a binomial, it holds for normal. So usually you might find that a normal distribution is written mu comma sigma squared. And I'm saying to you, if you find the sample mean of that, it will be mu comma sigma squared over n. So just look out for this reduction in the variance. The variance will get smaller if you take a sample mean. And that's worth knowing, because we're going to need to know it for our questions. Now this is a proof, first of all. It's quite a complicated proof. You could be asked this proof in the exam. I don't know if you will be, but you could be. So it says prove that x bar is the average of n independent observations of n. If that is true, then prove that the variance of x bar is this variance of x divided by n. So let's go through this line by line. I'd suggest you make notes on this. First of all, x bar is obviously the total of all the values we get divided by n. That's what x bar is. And if I divide each of them by n individually, I get this 1 over n x1 plus 1 over n x2 plus 1 over n x3 plus all the way up to 1 over n xn. Now I want to find the variance of these things. And we saw last time that if you've got a variable like this, you can find the variance of them individually. The variance of all of those bits, therefore, you can take it out. But when you take out that, it goes to the front of each one. 1 over n squared variance of x1, 1 over n squared variance of x2, and so on and so on. That would work for all of them. So far, so good. And you can see 1 over n squared effectively becomes a common factor. So I've taken 1 over n squared out as a common factor. And the variance of n x1 really is the variance of x. But this is also the variance of x. And this is also, and effectively you've got lots of variance of x's. And because it goes from 1, 2, 3 up to n, that's like n lots of variance of x. So there you go. Oh, the only thing is now I suppose it's n over n squared, which is why you end up with var x over n. And that's the answer. That's what we said it was going to be. We said it was going to be the variance of x divided by n. And there's our proof. It does work for all these situations. So here's an example of this. Find the expected value and the variance of a sample mean. Now this sometimes happens. They just tell you E of x is 6. The variance of x is 0.5. And I'm going to do this thing 25 times. Okay, so I'm expecting to get 6 whenever I do it. I'm going to repeat this. I don't know what it is. Could be I'm weighing fish. It could be I'm doing a binomial distribution, a Poisson distribution, or just some random event. But either way, I'm going to do it 25 times. And it says find the sample mean x bar. And not only do I want the expected value from doing this, and I want the variance as well. Well, the good news is the E of x bar will also equal 6. These things are always the same. And the variance of x bar, well, it would be the variance I had there, simply divided by 25. Now I don't know what 0.5 divided by 25 is. Let's do it on my calculator. 0.5 divided by 25 equals, it says 0.02. So I'm hoping the answers are going to say that. Yes, they do. So variance is 0.02, expectation is 6. Notice this one doesn't change, this one does change. So next example, it's a binomial again. So I can quite easily, it says x is binomial 24, 0.2. So I can quite easily, first of all, just quickly, E of x, using the formula NP that we should by now know, 24 times by 0.2 equals 4.8. And I can likewise use the second formula, which says the variance of x, what I'd expect to get is NP 1 minus p, which is 24 times 0.2 times 0.8. If I type it into my calculator, I get 3.84. So what's it say? I do 10 sets of this. That's the important thing. And so when I get my x bar with 10 observations, if you like, it will simply mean that E of x bar is 4.8. It's always the same, so it doesn't change. But my variance of x bar will be, well, this is where we have to just be a bit careful. It's 3.84. And I've got 10 sets of data, so it's divided by 10, and it's therefore 0.384. Okay, fair enough. I just spotted it. It says find the standard deviation. So the standard deviation of this lot, you always square root 0.384. So let me just do that now. Square root 0.384. Let's write this down. 0.6. Well, it says 196, so 620, I suppose. Okay, let's see what the answers say. Good, got them right. I think this is the last example. So the masses of randomly chosen male students from Cowley in 1946 were modelled with this distribution. So X is normally distributed 55, now it says the standard deviation is 2.2, so it's 2.2 squared. Should remember that. 4 students were chosen at random. Find the sample mean and the variance for these 4 students. Well, we should straight away say then that the sample mean of x bar, I'm expecting the E of x would be still 55. That's importantly, it's still 55, but the variance I would expect to change. So the variance of x bar will be the 2.2 squared. I've got 4 students, so divide by 4. So let's just do 2.2 squared. 2.2 squared divided by 4 is 1.21. So that's the variance, not the standard deviation, the variance. Okay, calculate the probability that the mean mass of these 4 students was between 54 and 56. Right, now this is the normal distribution. We can do this on our Casio Class Whiz or the Texas calculator. So we expect them to get 55, wasn't it? Yes. And they're saying, what's the chance of going up to 56, this down to 54? So, and I want this probability there. So if I just do this, I'm going to go menu, and it's menu 7. I want a normal CD. My lower value is 54. My upper value is 56. My sigma value, well, it's the square root of 1.21, so I might as well type that in. Notice I use this 1.21 value here. But I've got to square root it because it wants a standard deviation and the variance, and my mu is 55. Okay, and I've typed that in, and what it's come up with, my probability, my P equals 0.637 according to me. What's the chance of it being less than 53? So it's a very simple. I'm just going to, there's 55, there's 53, and of course I'm using still this idea that x bar is normal 55, 1.21. But I don't have to change very much actually when I press equals and go back to it. Now my lower value now, I actually now want this value. So I put my lower value down as a negative big number. So I've got like 10,000 job, negative 10,000. And my upper value is 53. Everything else stays the same. Oh, I've got a very small probability here. My probability is 0.0345. See what my answers are. Well, that's good because they both work. I think I've done those right. That's what we're going to do in class, exercise 8B. We'll get lots of practice at these different distributions. Some of the questions will be based on probability, but before you can do that, you'll need to know your mean from the sample mean, and your sample variance. So hopefully that makes a bit of sense, but we'll certainly practice it more next time.